Right. What we've been doing so far up to today, or up to yesterday, man, is what we call indefinite integral. Today, I want to discuss with you the idea of a definite integral. Obviously, you're not going to understand what is definite integral now as I'm saying it before you can compare with the indefinite integral. But what I wanted to be able to do by the end of this discussion is that you must have a meaning to a graph like that. Like for example, if I write here, let's say if I write here integral from A to B, f of x, d of x. So this is what we call definite integral. If you compare to what we've been doing before, with just an integral sign and a function there, and we integrated, and we know what we're supposed to do there. So when you see as integration written like this, with these two numbers there, we call them limits of integration. This is definite integral, and this is indefinite integral. Now, I'm not trying to discuss that now. I'm just saying at the end of this discussion, you must have a good meaning of what is happening here. What is the meaning of it? Shading there, the curve in relation to what is being done there. That's what we do. So how do we start? We start it this way. I'm not sure which system of. Yeah. Then we started this way. I'm starting with some ideas which I basically understand that some of these ideas should have used in early civilizations like the Egyptian architects along the Nile River. Remember, the Nile River flows from, I don't know, if you didn't do history, it's unfortunate, but I think if you did history, you must know about the Egyptian civilization, but maybe a bit of it in the Bible also can get it. So the River Nile flows from the Central Africa around the equator, and there are equatorial forests and everything. So the leaves of the trees in the equatorial forests are carried by the river to the mouth of the Nile River there, and they right close to the sea there. We expect the river to deposit the leaves which it takes from the equatorial forest, and then the ground there to be more fertile because of this rain. So it makes sense to have had the main activity there being agriculture. And then if you get a situation like that, let's say somebody wants to buy or pay some taxes for using this land to the state, whatever state was sitting there. Obviously, land is sold at a price which is charged per square kilometer. So if you do, even if you are paying tax, you pay tax for land according to how many square kilometers you are using. So then an idea comes, how do you calculate an area of a shape like this? You can put a straight fence there, and straight fence there, but this curve, this river, is not a straight line. How do you calculate an area between them? This is what takes us to ideas which give birth to what? Definite integration. This is how the story comes. Let's take that river as a curve of a function and put it on a horizontal system of axis like this. There it was turning vertical like that, facing north, but I just put it that conveniently on the system of axis like that. Now I want the area under the curve. Otherwise, the area between the river and this straight fence there, between those straight fences there. The only thing we can do at the moment, we can draw a rectangle from this part from here. We can draw a rectangle by complete that straight there parallel to that. Or go up there, up to the highest point there and draw another line there. Then basically I've got two rectangles. One rectangle whose width, I'm talking about the width from the horizontal to there, which is f of a. That constant there. And the other rectangle which is upper there, whose width is from here, there, that is f of b. Now if we were to say the area you are farming there is between so much and so much square kilometers or meters, you would need to calculate the area there, which is, let's say, upper area. I'll call it upper area for this part, which goes up to there. Upper area will be f of b, which is this height from there to there, multiplied by the length, which is b minus a. I think that is clear should be clear to anyone. And then the area which is between the river and the straight fence here is actually between this upper area and this lower area, which is lower area, which is going to be f of a multiplied by b minus a. So roughly that can give you an idea that if you know the price of land or the tax you pay for land per square kilometer, you can know definitely that I'm going to pay between what this guy pays and that what guy within this area pays. Then that gives you an idea. But if you want something accurate, then you should have a better way of approximating this area and then be more closer to what really you're going to pay in reality. I hope that makes sense. Do you understand what I'm talking about? Does it make sense to you? Okay. Now, let's come to this situation. What have I done here? The red line there is the one which was upper, and the red line there it was the one which was lower. What have I done? Now, instead of taking this whole length like that, I just decided to divide it into 1, 2, 3, 4 equal parts, roughly. And then what do I do? You can see that now the area which I'm covering, like for example for this position, is above what I covered before, because that before it was going up to there, but now it's going up to there. And there it's going up to there, and there it's going up to there, which means by making smaller divisions, I can have a better approximation of the area under the curve. And at the top there, I now not including this area, and making more divisions, small division, I can still improve on this approximation. Then where does this take us to? It takes us to something like this. Let's say I decide to have 10 divisions there. You see what I'm doing now? There are more rectangles underneath the curve to calculate area. But what I'm missing between the rectangles and the river is smaller, becoming smaller and smaller. Which means if I increase this number above 10, I'm still going to get smaller and smaller. But each one of these rectangles got an area which I can calculate. Like for example, let's take this first stripe here. I can take this A here, validate it, and get this point there on the curve. Remember, this point on the curve here is A, comma, f of A. That is the point here. But the f of A is where? F of A, I read it off there on the vertical axis. But f of A is, I said here A is equal to x0, so I can also say that is f at x0. Now, for that part, I can now say area, lower area, number 0. I can say that area which I shaded there is actually delta x. What is delta x? Is the equal distances between these divisions. So it becomes width times length, which is vertical here. So I get that area for that. So that is multiplied by f of x0. Then I can continue that, do the same thing. When I come here, I can validate 1 and that get the value there. I calculate this area. Maybe that color is wrong there because I've already got red there. Let me take a brown color. I calculate this area. So then I can do that with each of the stripes. Now, if I do that with each of the stripes, I can then add all of them, and then I've got an approximate area of that thing. But I hope you notice that the area which we started with right at the beginning was going up to there. So with all this included, but now it's not included. And at the bottom, it was going up to there. So if we look at this, area under the curve is actually increased from where it was here on the red line up to somewhere there, which means I'm getting more, a better approximation of the area which I actually need. Does that make sense to you? I'm talking to you guys. Do you see that the area below the red line is less than the area which I'm not covering with the smaller triangles? Hello, I'm talking to you. It's only natural that when somebody is talking to you, respond back, because our outcome is going to know whether you are following me or not following me if you are not responding. It becomes difficult to communicate. Right. So then, which means if we continue increasing this area, we're going to get a better and better approximation of this area. Now, where does that take us to? This takes us to the fact that if you now have all these rectangles at any other point there, I can say it's area. Sorry, I want to write in black. Area, lower area number K. It will be that delta X multiplied by f at X K. And you can see this will include this one, that one, the next rectangle there, the next rectangle there, up to 9 when I get to that one. Which means I'll do this from K equal to 0 to K equals to N minus 1. Because I'll not go up to 10, because after that I don't have it, I'll go up to this N. So then if I want the area under approximately the area, I've got to add all these values. So this is what I'm going to do. I'm going to say the sum. I hope you know that this sigma is a Greek S for sum. That is sum from K equal to 0 to N minus 1. Then I'll write the delta X f of K. Now guys, please understand me very clearly. The process I'm doing here is a simplified version of what normally happens. I'm just simplifying this thing to the extent that I think it's just to make you have rough idea of what's happening. Then later on we do examples, we must maybe have some trust of what is happening is correct. So now you have got this, adding all this thing. So like I'm saying, to get a better approximation, you need to increase n. Now if you increase n going towards infinity, this area will be growing and growing and growing, but it will never exceed the area below this curve. So which means actually the area below this curve is the limit of this sum as n is going to infinity. So I say it's 0 there. This is supposed to be infinity. So in this case, what I'm saying the area under this curve, I would like to say area UC for under the curve, is actually the limit of this sum as n is going to infinity. As you said, that the limit of this will be the area of the under the curve itself. So we say the area of that is the limit of that. But now if we stretch this n going towards infinity, making more divisions here, you must also see that delta x is also going to tend to 0, because you're having more and more divisions. So the length of delta x is going to 0. But that, by doing that, you are sort of stretching the sum. Instead of having a discrete sum of this plus that, you sort of kind of have an idea of a continuous sum. This is a discrete sum. These discrete areas add them. But now if that this thing tend to 0 is any time that you sort of doing that continuously. So when you stretch the sum, I say this is a Greek sum, S for sum, sigma. Then when you stretch the sum, what happens? This to the limit, you get a straight S like that for a sum. Remember the other day I said this is a question mark to say find the function whose derivative is an sign. Today I'm saying this is a sum, and I think this sum is relevant to what we're doing here also. So that's another meaning. So now we say that sum was stretching between A and the B of what? Of the function represented by this curve. In other words, the river which we took there as a river, we're interpreting it as a function f of x, so we get f of x. And to the limit as delta x going to 0, that will denote there as dx. And you call that a differential. So from this discrete sum, stretching the sum to the limit, we get what we call a definite integral. That's what I showed you at the bottom there, at the beginning there. So now, when you are having an integral like this between 2 points, that integral is actually calculating the area under a curve like that. And if this is area under a curve, or this integral is equal to numerically equal to the area under a curve, then you can give this number here, which you get here, a value which you get there, a numerical value you get there. Let's say n bar will give it units, square units. That will not matter whether you're using inches or centimeters or whatever. You know that Americans are still using inches. The British are also using inches. Some people are using centimeters. This is independent of what units you are using. Just to depend on the scale we are using there. So that is the thing. Hoping that is clear. Then we can come to this and now sort of write it in a more organized way, that when we've got something like this and we're integrating this function from A to B, we'll call this definite integral, and this value represents the area between A and the B, the area under the curve. All together. So what I'm going to do here, if you forget a little bit of A and B, just look at the integral sign. We say the integral sign was saying give the function which differentiates to this. Which means then we have to do exactly the same thing, find the function which differentiates to that. Then once you get the function, let's put it in capital letters and put it like that, as f of x. Once you've wrote that function, we'll write a kind of a stroke and say from A to B. And then what we need to know is what to do with this when you've got it. This is what we're going to do. I'm going to put it here, highlighted. This is exactly what I'm going to do. For your definite integral, you're given that between A and B, you do what the integral sign without the limit says. Find the derivative, the function whose derivative is this. You find the function, you write that stroke, then at the bottom there, write A. A is called the lower limit, and the B is called the upper limit. Then what you do there, check what you do there. You take the upper limit and evaluate it. Now you plug in this B in the function, you replace the argument, and you get a numerical value. Then you subtract the numerical value of the same function at A, like that. Then that value will be the one which will be numerically equal to the area under this function between A and the B. Exactly what we're talking about here. That value will give you the area between A and the B under the curve of the function which is under the integral sign. Am I making myself clear, guys? Okay. So then, let's go there. But now, same thing. This function which you got here, it must satisfy the same condition that when you differentiate it, you get exactly what is under integral sign. That's the condition. Listen to me, guys. It doesn't matter for me whether you come from Hong Kong, Honolulu, Japan, Malawi, or South Africa. If you say to me, you have done a little bit of maths to first year, second year, at tertiary, everybody in any part of the world will expect you to remember this. This is the ABC of what is called integral calculus. And this theorem, if I'm not mistaken, called the fundamental theorem for integral calculus. So you can forget anything. You can decide to even to not pass the course. But just if you want to give us evidence that you want to some maths at tertiary, I think you can have this. I mean, even some countries, they even do it at grade 12. I'm very, very sure of the fact that in DRC, Cameroon, they do these things at grade 12. There is, my witness says yes, yeah. Come again? Even calculate the volume. There is saying it. So I'm not saying anything. You can just say something to yourself. So that is the thing. So now what we need to do, let's do some examples and let's see whether this really makes sense with things which we know. Now check this. We're given, sorry, I've got a mistake there. I noticed to write there 2x. That 2x is this function which I've repeated there, a straight line. It cuts the y-axis at 0. Now, can I ask you guys, put your pens down, forget everything we've been doing in this chapter on integration, even differentiation, forget it. Let's take the very quickest mode of transport. Go back to our school, whether lower secondary school or upper primary, and think of area, calculating area of a triangle. Let's say between 0 and 5. Okay, let's put here 1, 2, 3, 4, 5. Now, let's get a line here to make this really look like a triangle. Let's get a line here which goes perpendicular to the horizontal and get there. Now we're at a point on the curve. That point there, it should be 5, f at 5. But f of 5, we can read it off from the vertical axis there. There, we're going to have f of 5. So we've got f of 5 there. Sorry, f of 5. No, that's not beautiful. F of 5 is there. So now, let's talk about this triangle. At school, not at tertiary, and you want the area of that triangle. Area of that triangle, it was always calculated as area of a triangle equals to half base times height. By the base, you can get that line as a base. This is a right angle, so this is the perpendicular height. So this perpendicular height is f at 5. What is f at 5? What's the value of f at 5? You need to evaluate this function. What is it? Evaluate this function. And just take a pen and evaluate this function. Give me f of 5. 10. Okay. So that's 10. Which means this length here is 10 units. You can choose your units. Now if you're going to calculate this area, you need the base. The base is 1 unit, 2, 3, 4, 5. So it's 5. So calculating this, we'll say half 5 times 10. Then half of 10 is 5. 5 times 5 is 25. Square units. Satisfied? Okay. Let's come to see whether this works with what we just said before. We said a definite integral will call upon a function which differentiates to this. This is a power 1. So we can use our power rule. Power 1 is different from minus 1. So we can say now equals x1 plus 1 all over 1 plus 1. Now we don't write a c there, just write that stroke. Then we say from 0 to 5. Then we say equals here. This is 2 and this is 2. 2 over 2, 1. So we end up here with what? X over 2. We do exactly the same thing, there's 0 to 5. According to our theorem, it says you must get that function, this is f of x, capital letter F of x. We must evaluate it at 5 and subtract the value of the same function at 0. But f at 5 is 5 squared. At 0 is 0 squared. 5 squared minus 0 is 0. But 5 squared is equal to 25. So unit squared. That is the thing. So that is an I put it there, illustrative example. This is an illustrative example to illustrate exactly the fact we're talking about there. That doing that kind of thing is actually calculating the area between the x-axis and the curve. I hope that is making sense. Okay, let's come to this one. What do we want here? Let me quickly complete this graph this way. Let's put a vertical line there. Why a vertical line there? There's a 2 there, above 2. Another line there. So, it's clear to everybody that that point there is a 6, F at 6. And our F at 6 is somewhere there. And then our F at 2 somewhere there. So then I'm expecting everybody in this class to be able to tell me what kind of a shape we're dealing with here. What kind of a shape is that, guys? These lines are vertical, therefore they are parallel. So what shape is this? Come again? A trapezium. Now, if we appeal to our, again, primary school or lower secondary school geometry and the calculations of area there, I think we all know that the area of a trapezium, area, I'll just write TRP for trapezium, is equal to half the sum of the two parallel, the lengths of the two parallel sides times height. But the parallel sides are A, this one, B, that one. But B is f of 6 and the A is f of 2. What is f of 2 equal to? Can you tell me? 4. So that is 4, which means that length is 4. F of 6? 8. So which means B is 8. And this is equals to 4. So coming to this formula, we'll say half, and sorry, the height, h, the height, is something which is more or less playing the role of delta x, the change of x from 2 to 6. What is the change there? What is the change in x from 2 to 6? 4. So what are we going to do? We're saying half height 4 plus 8. Half of this is 2. 4 plus 4? 4 plus 8, sorry, 12. 12 times 2, 24. So that area is expected to be 24 square units. So let's come and test whether this is valid here. Power rule 1, you come and say x squared plus integral of that 2x. Then we put a square bracket there. Now I'm not putting only a line because the line will only affect this one. So I want to show that I'm evaluating the whole function from there to there, from 2 to 6. Then I do this part, f of 6 minus f at 2. And it's clear to everybody that my f of x is that. Is that clear? Okay. So now let's do this. If we evaluate this, we're going to say 6 squared. Oh, there's a mistake there. What is the mistake? What is the mistake? There's something wrong here. Yeah, but don't think about differentiation now. Think about the power rule for integration. Isn't it x to the power n plus 1 over n plus 1? Yeah, so here it was supposed to be 1 over 1. So I think I thought about it but didn't write it, but you are there, you are watching, you are not taking responsibility of participating. That is a bad sign. Look at what I'm writing. I might think of something, but when I'm writing, like thinking forward, I might omit something. But please take the responsibility to say there's an omission. So that others are going to make a confuse ourselves. So they're what we got now. I'm saying it now because when I want to evaluate it, I know exactly what should be there, but I'm not seeing what is written there. Okay. So this is going to be 6 squared over 2. Now I'm evaluating where? At the upper limit. Plus 2 times 6. That's the value f at 6. Now it's f at b, upper limit. Minus 2 power 2 over 2 plus 2 times 2. We are done. Then you need to simplify this to get your number. 6 squared is 36 divided by 2. What is that? 36 divided by 2. 18. You need a calculator for that. Okay. 18 plus 12. This is 12, isn't it? 18 plus 12, what's that? 30. 30. You need a calculator to calculate that, I know. But anyway, I don't need a calculator because I've got my head used to calculating mentally some simple things like this. So now, 2 squared, you don't need a calculator. Or it's 4, okay? Divided by 2 is 2. Now this means you got a 2 here. 2 times 2? 4. Plus 2? 6. Okay, it sounds coming right now. Then you can put the square units. If you look at this number and what we got there, this is precisely 24 square units. So guys, I'm hoping that these illustrative examples, they are trying to make this idea of definite integral being numerically equal to the area under the curve of the function under the integrand is making sense. So now we can go further. I'll invite you to go and attempt this one on your own and see what you can get there. It is actually very, very interesting to know what is the area with a sine, standard cosine curve. What's the area which is just enclosed there in the first quadrant? Please try this at home. For now, I wanted to invite all of you to come to this one. I think there's a correction I should make here to this. There's a 2 there. This is what I wanted to bring to this situation. These are identities which I think you know, but if you don't know them, it's not a problem. What we're discussing is what is important, but you can go back and check these identities and make sure that you understand them. We start with this one, cos 2 theta is equal to that. Then make sine squared the subject formula equal to that. You will see why I'm bringing these two. And also this one, I think everybody knows that this is equation of a circle. That is the equation of a circle, which is what? Radius 1. Now if I make y substitute the formula, I think you can see that I'm going to get this kind of a term or expression with y subject to the formula. Separate on both sides x, you've got y squared. So it will be 1 minus x. So apply the square root, you've got y, then on the other side, you've got the square root of that. Now, if I try to integrate this according to what we know so far, you will see that this is not, cannot be power rule. I cannot choose power half because there's no derivative of the argument outside. Then this motivates something we call change of variables. Though I haven't discussed it explicitly, I'll use it here because there's something I really want to illustrate to you. So change of variables are going to stay. We know from polar coordinates that always x is equal to r cosine theta. But in this case, r is equal to 1, then you can say x is equal to cosine theta. I hope you agree with me on that one. Now x is now a function of theta. Now if I say dx d theta, I'll get this being minus sine theta, which is the same thing as saying dx is equal to minus sine theta d theta. Okay. So now what's new? If I go to this integral, because I failed to integrate it in terms of x, there is an option of changing variables conveniently, if possible, and do that. But once you change variables conveniently, you also need to change these limits. In other words, now you need to change. You need to say cosine of theta equals to minus 1. But cosine is minus 1. One of the angles is what? When theta is equals to pi. Do you agree? Remember, cosine is like this. Starts from 0, half pi, then it says minimum point there, and it goes up. And there, at minus 1 there, angle theta is pi. So what you can do here, you can start putting this thing here as pi. Then we go to cosine theta equals to 1. One of the first angles where cosine theta is equal to 1 is actually when theta is equal to 0. We're talking about that point, isn't it? So then we've got 0 there. So if we substitute this, just check this quickly. If you put x squared here, you're putting cosine squared. So you got 1 minus cosine squared, which is actually sine squared, isn't it? Then you apply your square root on sine squared, you get sine. Are we together, guys? Okay. So then you get here sine theta. But dx, you have declared here dx to be minus sine that. Then let's put our minus there, and now here I've got sine of theta d theta, which is the same as saying integral pi to that of sine squared theta d theta. I hope you are all there, guys. I hope you are comfortable with that. I just substituted accordingly this expression. If I change to polar coordinates, that integral is exactly that. But there's a problem here. It looks like we're counting reverse from pi to 0, isn't it? Now, I'm going to give you a certain property of integration which is very, very important, which you need to know. If you integrate from, you can try to those functions we tell there. If you integrate from a to b, a function f of x, and then we integrate from b to a, the same function f of x. I'm just saying, I'm leaving that dx just to quickly do that. What you're going to get, once you reverse the order, you'll find that this integral here is equals to minus that one. So now if I want this to be normal order, I would prefer to have this as integral from 0 to to pi. Now, because of this property, I've written it quickly there carelessly. I didn't put differential dx. I'm not doing that. I'm just trying to give that message quickly. So which means this sign must change. If we minus with plus, then I've got that. Then I've got cosine, sine squared theta d theta. Then we're done. Then we come here, we try to integrate this thing. We're at the cul-de-sac again. We've got a square power function, but we don't have a derivative outside, which means you cannot proceed. But for us to proceed, that's when we appeal to this identity. Do you see that? We replace sine squared with this identity. Then what we do? We say integral, and the half there is a number. We can take it outside the integral. Let's put half there, outside, and then it's 0 to pi. Then put here 1 minus cosine 2 theta d theta. Then we're ready to integrate now. Our half sits there, it multiplies whatever we get there. Let's put a bracket like that. Integral of 1. 1 is a gradient of a line y is equal to x. So the integral of 1 is actually x. In this case, our x is replaced by theta, so that is theta. Minus, here, if you say integral of this, what are we short of here? Can we integrate this without doing some manipulation? No, we can't. What are we short of here? The derivative of the argument. Isn't it? So then let's plug in the derivative of argument there. Let's say 2 over 2. So now if we read cos 2 theta by 2, we're having a derivative of a trigonometric function whose argument is 2, and the immediate derivative of that function is cos. Which function is that? Which function differentiates to cos? Sine. Okay, sine. So it will be 2 sine that. Let's put it there. 2, it will be half. Because this number half here, don't control it. It's going to be half sine 2 theta from 0 to pi. We now do the evaluation, which we did. We evaluated pi, subtract the value at lower. Let's leave our half, this one, outside again. And put a big bracket there and say, pi there, we'll have pi. Minus sine of 2 pi. Remember, theta is pi, we just replace theta by pi, we get 2 pi, divided by 2. That's the value of the function at the upper limit, minus the value of the lower limit. What is lower limit? 0. Put 0 there, 0. Minus sine at 0. 2 times 0 is 0. Sine is 0, 0. Times half 0. 0 minus 0. Then we close our bracket. Then we get in there and simplify. Let's see what we get. There is 0. Sine of 2 pi is 0. So here we're saying pi minus 0. The answer we get is pi over 2. Then we can call that square units. All right. Think about that. I'll give you a second to think about that. Think about that. Right. Thinking about that, guys, I think you can see that that's expression which got there. If we say x squared plus y squared equals to 1, it's a circle of radius 1 around the origin. So minus 1 is there, 1 is there. So if we're integrating that y equals to square root of 1 minus x squared, we want the area under this. Let's say take only the positive part, which is the principal square root. We want this area. This is our y-axis, this is our x-axis. We change the coordinates to what? To polar form integrated. We call that this area under the curve of the semicircle is equals to pi over 2. That's what we call. And we're saying this is square units. Okay, let's forget about the same area, the semicircle. Let's say this area, the radius is equals to 1. As far as you know, the area of a circle, any circle, area of a circle is equal to pi r squared. Sorry, what am I writing there? I'm trying to say r squared, I'm just writing out pi squared. That's a mistake. Pi r squared. In this case where r is equal to 1, then the area is equal to pi. But the area we're talking about in this integral, what it is half of a circle. Do you see that's half of a circle? Is that a semicircle there? It's half of a circle. So which means for that area, we would calculate half and it gives us this. What is it telling you? It's telling you that the area of a circle, that formula which we have at school, we say is the area of a circle is equals to pi r squared. Is confirmed here using integration. It's confirmed at least for r is equals to 1. If you want to see whether it's confirmed for r equals to 2, go and test it, do exactly the same substitution for what? For radius 2, for radius 3, or for radius of your choice. If you want the radius of your choice, say minus r here to r. You will see that this is exactly going to give you what we're talking about. So guys, with that, I think I've tried to make definite integral make sense to you. I hope this makes sense. So please go and sit down and re-engage with this thing and do some examples and make sure that you can, from tomorrow, describe yourself as somebody who has done integration, tertiary, and you can do definite integral, and you can use it wherever is possible. So the next example I'm going to give you is this one for a parabola from there to there. Also that one I'm going to leave you for you as a homework. Others for now, I wish to say thank you for listening. I hope you learned something, but if you didn't, I'm really sorry, it wasn't my intention. Goodbye. Meet you in the next session.